Okay, I guess I'm probably about ready to get started. Okay, first questions. Are there any technical questions or anything like this? Anything questions about logistics? Any questions about anything? Yes, questions. Okay, so the question is, what are you supposed to do when I ask you to design an algorithm? Okay, the first thing that's most important is an algorithm should have an idea at it. Okay, there is a reason why you came up with these. For all of these problems, there are certain times when a light should come on, and now you understand it, whereas before you did not understand it. That's what it means by an idea. For an idea, you describe your idea in English. Okay? Then, for any details that require more specification to really convince me you have the idea, I would, at that point, encourage pseudocode. Okay? But recognize that it should start with an idea or a picture that makes clear that what's in your head. So with almost all of these problems, there is one idea that once you have, boom, that's it. You can explain it and convince somebody of that. Okay? And a massive pseudocode will convince nobody. Is that understood? Yes, question.
When you write each question on a separate page and have our names on all pages, are we allowed to use written pages and type?
If you want, you can write them. If you want, you can type them. That much doesn't bother me. Again, the primary purpose for doing the homework, obviously we wanted you to convince us that you did it right, but the primary purpose is for you to be convinced that you did it right. Okay? And but bottom line is you can use handwriting or typing. Okay? You can use a mix of both if you wish. Okay. Any questions? Yes, question.
It's one problem per side of the page, right?
One problem per side of the picture. What is the problem we're trying to solve with the number of pages thing? Okay? It is very difficult for a TA who has to grade some subset of problems to wander through your paper and try to figure out where you have done this, right? It is much easier if they are on one side a sheet of a paper, and it is much easier if the logical groupings of the problems start at the beginning of each page. And that is why we are doing that. Yes?
Both partners put their names on the same...
Both partners put their name on the same sheet of paper. The goal is that there is one paper turned in per team. Okay? Not each of you turn in separate papers. Each team turns in one paper between them. Okay, and you argue among yourselves what that should be. Yes?
There's one coding problem on the homework.
Okay, there's one coding homework. I don't mean that necessary to be a real program. If you want to do that with pseudocode, that is fine. Okay? So don't worry about using a programming language for that one. Okay? I may have specified it wrong. But yes?
I probably already know the answer to this, but what if the question goes over a page length?
If the question goes over a page length, I'd like you to shorten it. What is the reason? Ultimately, this has to be read by a TA. The TA has comes into this, when a TA came into this class, they looked at the size of the people here, they said, my God, okay, this is a big class, it's very hard to read these things. Usually there is an idea. Remember, algorithms are ultimately about an idea. The idea, once you get it, is usually an idea that can be explained in a terse way, okay? And, and if you don't have it, fishing around for it isn't going to make anybody happy, okay? Yes?
What if we use the same piece of paper on both sides of that question?
Okay, I don't want, only on the front side of the paper, and I want you to keep the one page per problem, okay? Any questions? If it's taking you more, you probably don't really have the idea, okay? Any questions here? Okay? Any other questions about anything else technical or logistical? Okay, so the homework is due, the homework is due next class, as I understand it. 2 weeks from today is when we will have our midterm that will cover big O notation, searching and sorting, which is what we're going to start to get into today. And I've posted the homework 2's, the homework 2 assignment now. Don't get started on it till you finish homework 1. But I do encourage you to look at those problems before the midterm. The papers actually do after the midterm. But that's good business to look at those problems before the midterm. Any questions? Okay. Any other questions about anything? Yes?
Technical one. What's the difference between log squared n and log n? The whole thing.
What is the difference? A technical question. Okay, what is the difference between log n squared and log... Okay, here's why you get confused. I say, what's the difference between log n squared and log squared n? That's really how I would pronounce it. Okay? So here is a function, log of n squared. Okay? Where my parenthesis, if you notice, n squared is completely within my parenthesis. What does that mean? I'm taking the log of a number that is n squared, right? And that is going to be equal to 2 times log n. Does everybody probably remembers that kind of thing, right? Log of n squared is 2 log n. Now, what if I have a for loop that goes for I equals 1 to log n, and another for loop, j goes from 1 to log n. Okay, and I say print I comma j. Okay, how many times will this print statement be answered? Okay, yes?
Log n times log n. Or
Log n times log n. Does everybody see that? So that is what we usually refer to as log squared n. That's log n times log n. Okay, it's probably better to write it as log n squared. That would be probably the right way to write it. This is the way we write it, okay, out of habit. Yes?
Can't the notation log squared n also be log of log n?
Then you're saying, what about the log of n? That is actually written log n, okay, for the record. Okay, so sometimes people are interested in the logarithm of the logarithm. N grows fairly fast, log n grows slower, log n grows slower, okay, than that, right? So now we've got actually 3 different kinds of big O functions here, just as we got on the board. There is log of n, there is log of n squared, and log squared n. Which one of these is the biggest in the big O sense? Okay, yeah? Log squared of n. Does everybody agree that log squared of n is strictly bigger than log n? Right? And which of these is the slowest in log n sense? In big O sense, yeah?
log of log n.
The log of log n grows slower than log n. Okay? So in fact, there are these 3 functions. Now, for most of what we're going to be doing in here, if you take a advanced enough algorithms class, you will see algorithms that run this fast, and algorithms that run this fast, and algorithms that run this fast. Okay? And there's even some other more baroque complexity functions. But for the most part, we're going to be worrying about just log n in here. And the important thing to see here is, again, log of n squared, or n cubed, or n to the 10th. All of those boil down to big O of log n. Any questions about that? Okay, so these functions do have meaning. They're a little esoteric, and for most of what we're going to do in here, they're too esoteric for us to deal with. Okay? But you can rest assured that there are algorithms where these are complexities that are interesting algorithms, even if we don't end up talking about them in here this semester. Any questions about that? Okay? Any other questions? Okay, so let's talk about the daily problem. Clearing. And the problem of the day says, let's read what the problem of the day says. We are given as input a sequence of 2n numbers. Okay? We want to have a number that will partition them into pairs, meaning a total of n pairs, such that we minimize the biggest sum of a pair. Okay? So let me think what that means. Here's an example. We've got 4 numbers here. My claim is that there are 3 ways to pair these numbers up. Why are there 3 ways to pair these numbers up? Can anyone come up with an argument that there's not more of them in this particular case? The item 1, which is first in sorted order, is going to need a buddy, right? And once you specify what its buddy is, the other pair is determined. That's why there's only 3 pairings in this case, right? For a larger n, there's going to be an exponential number of possible pairings, right? But here we could pair 1 up with 3, 1 up with 4, 5, or 1 up with 9. When we do that, the other numbers are given in the other pair. And if we sum up each pair, we get sums of, in this case, 4 and 14, 6 and 12, 10 and 8. Which is the one that minimizes the largest sum of a pair? Which one is the one that minimizes the biggest number in the pair? That is the one, this one, the biggest number was 10. Here you had 12, here you had 14, right? Here we're looking for, so which partition is the one that we're looking for? We're looking for this one. Any questions about that? You can tell I've got worried looks here. Okay, any questions? Why might one want to do this? Let's first forget about the algorithmic thing. Why might you want to take a bunch of numbers and pair them up so that you minimize the maximum sum of a pair? Can anybody come up with an application? Yes?
Maybe these are x and y components of forces, and we want to sum them up in a way that minimizes the maximum force on some.
Okay, so you're thinking maybe some forces thing. Can anybody come up with any other case? Yeah. Yes. What?
That's not the real one.
Team making makes sense to me. Let's imagine this completely hypothetical algorithms class where students were encouraged to do homework in pairs, okay? And people had to be paired up to do this, right? And suppose, let's say, every person in the class had a score measuring how good an algorithms person they are. You can think of it as an IQ, you can think of it as GPA, something like that. What would be the fairest way to pair things up so that no team got too much of an advantage? Okay? Does everybody see that the sum of the skills of the team represents the power of the team? If I want to minimize the maximum sum of a pair, what am I really saying? I don't want to create a super team. I don't want to create a dream team of algorithms people, right? I want to try to make these teams as fair as possible. Okay, does that application now start to make sense? Okay, any questions about that? Okay, any questions about pairing up a team? Okay, so how can we take these n people, ranked 2 n people, with each of which with their algorithm quality scores, and make a pairing that would be as equal as possible? Okay, any ideas? Okay, yes?
You could sort them to order, first of all.
So you're proposing that what I should do is to sort them in order. So I sort them from the best algorithms person down to the worst algorithms person, right? And now what?
And then you pair up the middle 2, so like n and n plus 1, and then the next 2 out, and then the next 2.
Okay. Does everybody see? This is what she is proposing, right? Does everybody see that? The best algorithms person is going to be paired with the worst algorithms person. Okay? Does everybody see that? And then we're going to pull that pair off, and we are going to end up with that. Okay? Any questions about the procedure? Okay. How many people, not even any questions, how many people understand the procedure that was proposed? Okay? How many people like that algorithm? Think that's probably right. Okay? Why is it right? First of all, there's 2 separate questions with any algorithm. First of all, is it right? And why is it right? That's probably the bigger question. That's undoubtedly the bigger question. What is the running time of this algorithm? Let's first answer the dumb question. What is the running time of this algorithm?
O of n log n.
O of n log n. And why is it n log n? We have to sort the n things, and that took n log n time. And now we have an array that is sorted with these guys in them, right? And now the question is, how much time does it take to do the pairing?
Linear.
Once they are paired, it's a linear thing, right? 4i goes from 1 to n. Match I with element 2i minus 1, right? So this is going to be n log n plus n, which is n log n, okay? The bigger question is, why is this right? Okay, can anybody propose an argument? Yes?
Well, the argument I proposed when I submitted this was basically a recursive argument. That is that if you took the best person and the worst person out of the list, then you could apply the same argument to the new list.
Okay, so you're saying a recursive argument, but you're really giving a recursive description of an algorithm more than you're giving me what is really an argument, the way to think about it. Yes, how would you do it?
You take the maximum number and add it to any other number. You would have sum larger than anything else if you took the maximum plus the minimum.
Okay, so what you're trying to tell me is that, okay, let's just go and take a look at this thing. And, oh my goodness, what do I have here? Okay, we have a visitor here who has planted something. That is my daughter Abby over there. Okay, so, okay, thank you, Abby. Okay, now let's go and think about this a little bit. Your argument was you have them sorted from biggest to smallest, okay? And you're saying that if I took the biggest one and I paired it with anybody else, that sum would be bigger, right? Is that a problem? You say yes. Is it a problem? Yeah?
Yes, because we have to minimize the maximum.
You're saying yes. I'm going to say not necessarily, okay? What happens here if our middle people happen to be m minus a tiny bit and m minus 2 times a tiny bit? You see that all these numbers, the class happens to be, since this is a made-up problem, filled with people of a lot of algorithmic ability. Okay? And it could very well be this sum, if I pair this guy up here, let's say that this person's of skill 0, this person's of skill 1. Suppose these people are all of very, very high skill, big numbers, right? Does everybody see that pairing this guy up with that one may not create any kind of a bottleneck? Because the sum of the middle two entries is going to be the bigger one, right? So it's not necessarily wrong to do that. You haven't proven to me that I'm wrong, okay? How many people see that argument? Okay? Now there's a kernel of an idea here, but yeah, what else is there?
I was just saying I see the argument.
Oh, see the idea. Okay, good. Any other ideas how you would prove something? As far as I am concerned, to a certain extent, computer scientists know 2 ways to prove things. How do you prove things? Okay, what ways do you know how to prove things? Yes? You can use induction or, yeah?
Construction, existence proof.
Construction, existence proof, maybe they know 3. I think of contradiction is the way that I would like to think of it, as my strategy of what you're doing. You're saying to me, what is a contradiction proof doing? It's saying, suppose I am wrong, okay? So in this case, what would you be doing? If I am wrong, what does that mean? That means somewhere out in the world, there is a group of, a class filled with 2n algorithms people, that if you do this procedure, okay, the biggest value, first of all, before I even get to the proof, again, the argument that we had before, where is the biggest sum? It could be the outer sum by this procedure. It could be the inner sum by this procedure, right? So there's no guarantee that, or in advance, that one of these sums was the one that was the winning one, right? Does everybody see that? So suppose there wasn't a counterexample. What does it mean by if there's a contradiction? That would mean that you took your numbers, you did your pairing algorithm, just like we said, And somewhere, here to here, was the biggest pair that you found, right? However you pair them, there's going to be a biggest pair. That's what we're trying to minimize, right? But suppose you tell me, no. I have another way to pair them up, and this plus this, let's say, is the biggest pair that I get, and it's smaller than your pair. That's what a counterexample, an argument, a contradiction would be. If you could show me that the biggest pair you got by pairing up this example was better than mine, okay? Now, how do we know that this can't be a problem? Okay? Yeah?
Because for the example you gave, both of the numbers being paired up are larger than the ones.
Okay, so in this case, this obviously can't be a counterexample to me. Because if this was the biggest pair you had, the sum, this number is bigger than that, and this is bigger than that, right? But how do I know, for example, they might not have done something like this? This is probably a better example. Maybe this was the biggest pair possible. Okay, suppose they told me I paired it up and this was the biggest pair possible, right? The sum of these is certainly smaller than the one you got. Is it possible that this was the biggest pair they got?
No.
No. Why not?
Because it's sorted, a bigger number, it could be equal to, but a bigger number would occur if you were to go to a higher number because they come before it. And
Well, yeah.
If you had made that pair, then the maximum would be paired with something bigger than the minimum, right?
Right, so now what am I saying here? Right now I've got, you have to know, there's sort of an argument, you have to argue that there's something else has to have happened. Could this have been the biggest pair? Well, there are a certain number of numbers that are bigger than this one, okay, and a certain number of numbers that are bigger than this one. If I have any pair, if there has to be any pair that where both of them are bigger, then that means it's not possible for you, right? And so let's think about it. If this is what you said the best pair was, I've got here a bunch of numbers, all of which are bigger than this. Does everybody see that if this was your best pair, all of these numbers had to be bigger than the one that was the biggest in your pair, right? The only way the sum of this which one of these guys got married to, this plus its partner was less than this total. If all of these got matched to somebody smaller than that, does everybody see that? But you can't do that, right? Because there are more numbers up here that are bigger than your bigger target than there are smaller numbers than your smaller target. And that will be the case unless you manage to pick the exact same number above and below in your case. And how do I know you didn't do that? Well, that's what her algorithm did, right? Her algorithm deliberately paired it up so that the ith largest got married to the ith smallest, right? If you had a counterexample, you had to have done something different. But you couldn't have done something different because there's not that many bigger and smaller ones available. Yes?
Well, what if you started where the middle was somehow the average of all the numbers?
Start at the average of the numbers. Okay, what about the average?
You're going to end up with, like, it's going to be lopsided, but isn't it going to be better than this?
Well, wait, if you start at the middle, notice that pairing from the middle is in principle not any different than pairing from the outer, from biggest to smallest in, right? Because once you take the best and the worst, best and the worst, best and the worst, you're eventually going to end up with the two middlest ones. So I don't know if hands see why...
I'm saying instead of starting at the median, I guess
Yeah.
that's what she was saying, start at the average, and then you're going to have...
Start at the average. Well, the average is a weird thing, okay? If the average is Bill Gates, okay, a average of salaries and one guy is Bill Gates, right? Then you've got a weirdly different structure to where the biggest pair is than the average if they are all almost equal.
But you've got a much better game.
Okay, bottom line is I am happy with the median, with this pairing. Why? Because it guarantees me the right thing. Okay, we're going to talk more about something different afterwards if you're concerned. But do you see what the argument is? Okay, if it didn't give you the right thing, then you show me what the right thing is, and I prove that couldn't exist. Okay, because I could come up with in your assignment there had to be one bigger than the one you're trying to foist off to me as the biggest one. Okay? How many people understand the correctness idea? How many people don't and have a concise question? Okay, how many of you have a question even if it's not that concise? Okay? Any questions here? Okay? So what is good? Okay? This is an example of a couple of things. One is an example of how sorting can be used to solve problems, which is going to introduce why we are caring about sorting. Okay? It also introduces us to the point where there are algorithm problems, where correctness is a slippery thing. In this case, I think people would have come up with this algorithm fairly easily, right? I think most people locked in a room would have come up with this algorithm. Okay? Now, recognizing that it's correct and really proving it's correct, that's where there is some subtlety. Okay? Any questions? Okay? And again, what I would be doing first is look for counterexamples. Look at what happened in the case where they were really skewed. Okay? Look at the case of where they were all equal. Okay? And see if it sort of does the right thing. Any questions? Any questions about this problem? Okay, good. Okay, so let's move on a little bit to this notion of sorting. So sorting is one of these topics that as an algorithm professor you like to talk about. As students in my class, they never like me to talk about it, okay? Because they think they've seen sorting so many different times. What else can be said? Why is it that computer science professors never stop talking about sorting? There are three reasons, two of which are good, okay? The first is that there is a factoid out there that said that mainframe computers historically have spent more time sorting than any other single thing that they do. Okay, this is undoubtedly still true of mainframes, the ones that do big data processing tasks. It's undoubtedly not true if you factor in video games, right? Because video games are these computers and they're busy graphics. As one thing is, rendering somebody getting their head cut off and stuff like this. That requires a lot more cycles these days. And by that measure, that's not really the real reason you need to study sorting many times. The two reasons that are interesting is, one, sorting is the best studied problem in computer science. And there are a lot of different ways you can go about doing it. And they're all based on different ideas, and they're all very, very interesting. Well, not all of them are very interesting, but it is surprising how interesting they are. One of the most interesting books that I have ever read, which I'm going to refer to you guys, how many people here know who Don Knuth is? A few of you. He was sort of the old algorithms god, okay? And he wrote what was a book called Volume 3. He wrote essentially a three-volume series of books. The third book is about sorting and searching. It's an entire book just about sorting algorithms. All the programs are given in assembly language, okay, for God's sakes. And it is still an amazingly interesting book to read, okay? And I strongly encourage you sometime to take a look at this thing. Because it's about all these different approaches and analyzing them, and you get into some amazing mathematics and some amazing ideas. And that's one reason why computer scientists are excited about sorting. Yes?
He's still writing the fourth book.
He's supposedly still writing the fourth book. My fourth book will be out. My fifth book will be out before his fourth book. That much I guarantee you. Yes. What? This is The Art of Computer Programming. For those of you, there's a series of books called The Art of Computer Programming. Everyone should go to the library and look at this, just to sort of say that you've held it and to look at it. Okay? But the other reason why I'm going to talk about it, it's not purely hero worship, is that most of the ideas that come up in algorithms and data structures, to really understand these ideas, there is usually something in sorting that can help teach these ideas. And so it provides a good laboratory to discuss them. Okay, we're going to talk about divide and conquer. as an algorithm technique. I'm going to talk about randomized algorithms. We're going to talk about lower bounds. And these are best off done in the context of sorting. So I expect that you have seen most of these algorithms. I expect you have probably programmed many of these algorithms, okay? But I'm going to try to go more into the analysis or the ideas as to what makes these things exciting. Any questions about why we're going to talk about sorting? Okay, so we shall talk about sorting. Bunk. And again, we've talked about big O notation and complexity and stuff like this. The fact that sorting can be solved in n log n time instead of n squared time is a really big deal, okay? And so we should respect this right now. If you looked at something like bubble sort, I think on average there are most of the standard n squared sorts might take something like n squared over 4 steps on average, okay? If you compare that to n log n for a large n, even a modest size n, okay, 100,000, this is 2.5 billion operations. This is a few million operations, okay? So to sort 100,000 names was the number of names in the telephone book in a small city or a modest-sized city, okay? You could not live in a world of telephone books if there was not an n log n sorting algorithm. Does everybody see that? And let alone you could not live in a world of, a Facebook and all these other things for bigger things if we didn't have efficient sorting, okay? So the fact that there is an n log n sorting algorithm is something that we should respect and be grateful for. Any questions about that? Okay, so that is a fundamental big lesson. What else is there? Kabunk. More to the point, the fact that we can sort in n log n time is what gives us the power to do lots and lots of other things in n log n time. The fact that we could do our pairing problem in n log n time is only because we had n log n sorting. Does everybody see that? And knowing that you can sort something as an elementary step helps you solve lots and lots of other algorithm problems. So probably the most important thing I will tell you during this whole unit on sorting is just to remind you of all the applications that sorting has algorithmically. Okay? You can do better as a dumb rule when someone gives you data. You have an algorithm problem. What should you do with it? Usually, the first thing to do is to sort it, okay? Or at least the first idea to throw out to your partner is, hey, maybe we can sort it, okay? Because that pays off, that is fundamental to a lot of different things. So let's look at applications of sorting. Now, what is probably considered to be the killer app of sorting is, looking at whether an item is in a dictionary, or in particular, a sorted dictionary. How much time, now what do we use binary search? How does binary search work? We look at the middle element in sorted order, right? Based on this, if the element is before, if we're looking for a key k, we compare it to the middle element. If k is bigger than the middle element, we know it lies on this side. If k is less than the middle element, we know it lies on that side, okay? In one step, we have halved the size of the problem. So what does that mean? What is the running time of binary search?
Log n.
Log n. You have n elements. In one test, you have halved the size of your space. Does everybody see that? And how many times can you take n things and halve it till you get down to 1?
Log n.
Log n. Okay? Any questions about that? Some of you are still nervous. Anybody wants to know where the log comes from? This is the important question. Any questions? Okay? So binary search is a very useful tool. And actually it occurs in a couple of different things. Again, maybe I'm now wandering a little bit. How can you find, let's say, here you have when you took, let's say you wanted to find the square root of a number. Right? Suppose you want to figure out what is the square root of n. I'm talking about numerically. How do you compute what the square root of n is? Okay? Some of you say it's easy. I punch a button on my calculator.
Well, how does the calculator?
How does the calculator do it is now what I'm wondering about. How can you find the square root of n efficiently? Yeah? Do what? Newton-Raphson method. These are big, complicated words. I don't know about Newton-Raphson method. But I do know about binary search, right? What does binary search say? You look, you have a point that's to the left of where the number is. Give me a number. Let's say we want to find the square root of some positive number, n. Big positive number, n. Can you give me a number that is less than the square root of n? Okay? What's a number that's less than the square root of n? 1 or 0, right? Let's say we're looking for square root of, a billion. What is the square root of a billion? I know it is somewhere between 0. I know it is somewhere between 0 and a billion, right? How can I find out what that square root is? Can I use binary search? What if I compare the middle of this interval, right? What's the middle of the interval between 0 and a billion? Half a billion, right? If that's the square root, half a billion would be equal to half a billion, right? If half a billion squared is bigger than a billion, then the root lies on this side, which is its case, right? If half a billion squared was less than the square root, then the square root would lie on the other side. Does everybody get this idea? How many people don't see it? Okay? Not sure if I'm getting people here. Let's compare it exactly. If I know the square root, I'm looking to find the square root of n. Suppose I know it lies somewhere between a and b, right? What does that mean? That means that a squared is going to be less than n, and b squared is going to be greater than n, right? That's what it means for the square root of n to be between that. If I take the midpoint of this interval, which is a plus b, if I square it, depending upon the relationship between that and this number, okay?
Isn't it a plus b over 2?
A plus b over 2 squared, okay? That's the average value, right? The midpoint, the median, okay? Either this value is going to be bigger than n or less than n. And based on that, I either know that the square root lies here or the square root lies here. Okay? How many people get that idea? So how much time does it take to find the square root? The square root of n? Log n. Okay? Any questions about that? Yes?
There's a problem about precision.
There's a problem here about precision. Well, let's say I'm looking for the integer between, I'm getting it to the nearest integer, this will take log n, right? You want more bits? Well, that's equivalent to multiplying your number by 10 to the something to make it a bigger integer. Actually, maybe I'm not quite saying that right. We agree you could keep bisecting this interval smaller and smaller, okay, to get whatever precision you want, right? Right? And so you could, in fact, use this to get the precision as far as you want, but if you're willing to find the integer square root, this will do it in log n iterations. Any questions about that? Okay? So that is the power of logs, that is the power of binary search. And the reason for searching binary search works is because keys are in sorted order. Any questions about that? Okay? So that's an application of sorting. Suppose I am given a bunch of integers, okay? And I want to find which pair of integers is closest, okay? Let's say I have a bunch of numbers, and I want to figure out what is the two numbers that are closest in value, okay? So, I mean, what might be an example here? Suppose I gave the numbers 5. Oops, let's try this one. Let's try this thing. 5, 23, 13, 8, 2. Which pair of numbers in this thing are closest in values. Okay? Yeah? 5 and 2 differ by 3. Does everybody see that? And 5 and 8 also differ by 3. Fortunately, this was 8.1. Okay? And so that's a little bit bigger. Okay? Any questions about that? Okay? So, how do we go and find which, can someone give me a non-sorting algorithm, given n numbers, to find which pair of numbers are closest? Okay? Yes.
Brute force, test all pairs, and then find the minimum.
For I goes from 1 to n, for j goes to 1 to n. What is the difference between, the absolute value, if you wish, of the difference between a sub I and a sub j if I and j are different? Right? Because I and j being the same, there'd be no difference, right? So in n squared, you would be able to find which pair is closest. Does everybody get that idea? Can anyone give me a faster algorithm? What is the first thing to do? Yes.
Sort it.
Sort it. It solves everything. Now, how long does it take to sort it? N log n. Now, once it is sorted, what do you do?
Compare one number to the next and basically save an integer that is that number and then compare it to the next number to the next and just...
Well, what is the property that we want from the sorting? After the sorting, what we claim is that the nearest pair of numbers, the closest pair of numbers, will be neighbors, right, in sorted order. That's what we're claiming. Why does that have to be true? Can anybody give me an argument why, after you sort it, the nearest pair of numbers are going to be neighbors? Anybody? Yes.
Because if there were two numbers
No.
that were closer together, then there would be one in between.
Does everybody see it? It's sort of a proof by contradiction. You're saying no, 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 okay? In fact, this x and y are the closest pair of numbers, but when you sort it, there's a number z between them, okay? And you're saying that can't be the closest pair of numbers, right? Because both xz and zy are closer, right? See how we're using a proof by contradiction argument? The reason we know that the closest pair of numbers has to be neighbors is suppose not, okay? Then we would have a situation where somebody was in between. And then can these guys really be the closest pair? No, no, no. One of these two has to be the closest pair. Any questions about that? Yes?
Well, could you just say if it's sorted, and then if you have a case like that, where there's a number in between which is actually closer, then it's not sorted anymore. Then it goes against the definition of what it means to be sorted.
Well, actually, I'm not sure I would interpret it that way. The definition of sorted implies that the closest pair of numbers are going to be neighbors. Okay? Now, the contradiction is not that you said you would sort it and you didn't. Your sorting program had a bug. That's not the algorithmic contradiction here. We assume we sort it. We can assume we sort it correctly. The property we then need is that the closest pair of numbers have to be neighbors in sorted order. Okay? For the sweeping argument that this gentleman was suggesting, compare the first and the second with the second and the third with the fourth. This will find the closest pair if they are sorted, because the closest pair will be always must be next to each other in sorted order. Okay? That's where the correctness comes from. Any questions? What is the running time of this? It is n log n to sort. How much time does it take to sweep to find the closest pair once they are sorted? Yeah? Order n time, right? You're comparing 4i goes from 1 to n, I to i plus 1, right? What's the absolute value of the difference? Okay? Any questions about it? N log n for finding the closest pair. Kabunk. Now, sometimes maybe a more common sounding problem, okay, is one that says you're given a file of n names, okay, and you want to find out whether they are all unique or if there are duplicates. What might be an application where you care about finding duplicates in a file? Can anybody think of some time when they might have to do such a thing? Yeah?
Assigning email addresses to people.
assigning email addresses to people, assigning email addresses to people. I'm not sure why that would be a duplicate thing, because when I think, if you think of your problem, somebody goes and wants to get a new account, okay? That's really checking to see whether the next problem, the one that they want is already in use. That's a data structure thing, right? Look up, oh gee, I want to be skeena@gmail.com, right? You go and try to reserve it, and they say no, 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 right? The reason is because they did a lookup in their database and said skeena@gmail.com is reserved by somebody else. So that's not really removing duplicates or identifying duplicates. Yes?
Cleaning up duplicate files on a computer?
Cleaning up duplicate files on a computer, that might be the case. Let's say maybe. That's not the one that I'm thinking. Let's try.
Version control system.
A version control system. The case that I am thinking about is building up a spamming list. Okay? Again, there's a lot of these cases here. Which one to me makes sense? You can imagine that you cull email for all your email addresses from a variety of locations, right? You want to identify, maybe you have, professors who you've taken classes from, and somewhere in there skeena@gmail.com is. And maybe you were a member of the programming team here, and there skeena@gmail.com is. You can concatenate these things. If you want to come up with a unique list of who is it that you want to send mail to, you want to remove duplicates. How many people does this make sense to? Okay, are there any confusion as to why you would want to do this? Okay, it's actually a pretty fundamental kind of problem. Okay? So how can I take n items and find out whether there are any duplicates? Okay? Can someone suggest a slow but correct algorithm to take a file with n names in it and identify if there are duplicates? Yes.
Check the first element with every other element.
For I goes from 1 to n, for j goes to 1 to n. Is element I equal to element j? If so, you've got a duplicate. Throw one of them out, right? What is a faster, sleeker way to do this? That's a yes in the back. Sort the array and then compare neighbors. Does everybody get that idea? Once they are sorted, what is the closest pair if these things were sorted? Well, the closest pair is if they are identical. Is everybody right? So when you sort something, all things that are the run of things that are identical will be stuck together, right? So it is now a special case of what we did before to make a linear sweep through these things and try to find out, look for each block of contiguous names, okay? And only keep one from each block. Any questions about that? Yes?
Can you also use a hash function to
Could you use a hash function for this? So in fact, one way you might do this is you build a hash table on the n keys, and for each key you hash it and you look in the bucket and you say, is there anybody else in my bucket with the same value as me? Right? And that would be a perfectly good way to do it. Okay? On average, in practice, if you got lucky, that should be order n time. Does everybody see that? Because you build a hash table on the n names. Okay? In general, if you got lucky, each bucket in the hash table will have almost nothing in it, right? When you hash a name to the thing, you look to see, is that name already in the hash table bucket? If so, delete it. But what happens if you get unlucky with your hash function, yeah? Then it is n squared. Everybody gets tossed into the same bucket, and now you must sweep through it. Okay? So in the worst case, you have a lousy hash function, or you get extremely unlucky in who's in your database, and everybody got hashed to the same bucket. So n squared in the worst case, n in the best and probably likely, if the world isn't out to screw me, case. Okay? But in the worst case, it is not n log n. Any questions here? Okay? So pragmatically, not a bad answer, but as an algorithm design thing, not really what we're looking for. Okay, good. What about finding the mode of a set of integers? Okay, what is the mode of a set of numbers? Actually, Abby, do you know what the mode of numbers are?
Yeah, it's when you take how many is the most of them all.
The number that occurred most frequently. That's exactly right. Okay? So give her a round of applause here. Yeah. Okay. So the mode of a set of numbers is the number that occurs most often, right? In this case, all of you have salaries that you may be earning now. What is the mode in dollars per year that you guys are making? What's the most frequent number? Probably 0, okay? But you understand that, right? Okay? Now, how can we compute, given a set of n numbers, what the mode is? Okay? Yes?
Sorted, and then when you're going through, check.
Sorted, and now all the identical numbers are broken into blocks. Does everybody see that? Now the claim is in a linear sweep through this. You can identify where the start of a block is and where the end of a block is. Does everybody see that? Okay? And, again, does everybody really kind of see that? Again, you start with the first value. You then have a loop while the next value is the same as this. Keep looping until you get to the point where you're just past that block, right? And now the index of this minus the index of this tells you the size of that block. Does everybody see that idea concretely? Okay? In an order n sweep through this thing, you can break it into runs. The size of the largest run is the mode. Any questions about that? Okay? So this is something that, again, requires sorting to compute. Any questions about that? Any questions? Okay? One thing to note here is, actually in general, if you have a sorted array, and you want to find out how many times a particular value x is in that array, how could you do this? Okay? Suppose you have a sorted array of things, and you want to figure out how many times x is in that. Can anybody give me an algorithm to find that? Okay? Yes.
Use binary search to find the first occurrence of x.
So binary search to find the first occurrence of x. Now, first question I'll tell you is I don't offhand know how to find the first occurrence of x. What I do know, let's just at least to start, I do know how to do binary search to find an x. Does everybody see that? Once I have an x, how do I find how many x's occur? Okay, yeah?
If you're starting with nx, you have to go back and forward. But if you start with binary search for x minus 1, you can have to...
Okay, so the first thing to note, the answer that people might come up with, well, once I find an x, I can walk until I find a place where the block ends, right? The guy next to it is either going to be, if it's an x, the block keeps going, right? And I could walk until I see a transition where this is something less than x. X minus 3, let's say. And this is x plus 5. Right? The trouble is, I might have to walk over a large number of elements. Right? If the entire array was filled with x, how much time would that algorithm take?
Linear time.
Linear time, order n. Does everybody see that? So if there's a lot of ties, it could be that the walking step would actually be bigger than the actual searching step. Okay? So how can we solve this problem? Yeah?
Why don't we use a binary search on the left side and right side to find the x value?
So binary search on the left side or right side. How would you search for something just less than x? Okay? Whenever you do a comparison, I ask myself, if the element is less than or equal to x, less than or equal to x, it's going to be on one side. I look for something I do a search, and I'm going to guarantee that this element that I'm searching for is just less than x. How do I search for something just less than x? If the value is x or less than x, greater than x, I say it's less than that. And if it is strictly less than x, I say that it is greater than it. In that case, the thing that my binary search would find is the exact crack between x and something less than it. And by doing one binary search to find that, and one binary search to find this, I could then subtract those indices, and that would tell me where the number of times this occurs. How many people get that? How many people don't get it and want me to explain that again? This is not an unfair question. Any questions? Yes?
How about hash map?
How about hash map? Now, what does hash map do? Hash map, as far as I know, is just a hash table. Am I correct? So if it is just a hash table, what is going to happen? Okay, if I want to find out how many times x occurred, I could hash everything and look at the bucket that contains x. But it might contain everything in the universe there, right? The bucket that x got hashed to might also be the bucket George Washington got hashed to, right? So I've now got to go through the elements in this bucket and remove anything that is not x, right? And if so, then that might be that there's going to be, there might be, an arbitrarily large number. That's why, in practice, a hash table might not be a bad way to do these things. Okay? In the worst case, it's a bad thing. Any questions? Okay, good. Talk to me. Bunk. How do we find the median of a bunch of numbers? Actually, Abby, do you know what a median is?
The median is when is the middle number, like when you take the biggest, the smallest number, and you make it in a line to the biggest.
Right.
And then you cross out on the biggest.
Is everybody the same number above as number of people things above it as below it? Okay. How do we find the median of a set of numbers? Okay. How would we go about algorithmically? I give you a set of numbers. How do you go and find the median? Okay, yes?
Sort it first.
Sort it first. Okay, and once it is sorted, okay, what do?
Take the median.
Take the element that's in the n over second position. Does everybody see that? So once it is sorted, it takes order constant time to find the median. Okay? That gives us a total n log n algorithm for sorting, for finding the median. Does everybody get that? In fact, unlike the other problems in here, there is, in the worst case, an order n algorithm for finding the median. But that, in fact, relies on sorting-like ideas. We're not going to, we may semi-talk about something in here like that. Okay? But the fact is, again, by sorting, you get an easy answer to this thing. Any questions?
Did you say log n?
There is an order n algorithm. So the sorting is n log n plus constant time to look the element up. That's the algorithm that you proposed. That is what I would be doing in practice. Now, in fact, there is a very clever order n algorithm for finding the median. Okay? But in fact, the ideas that it relies on are from really understanding one of the sorting algorithms we're going to talk about in here. Any questions? Okay? That's a tricky thing. Okay? But sorting gets you most of the way. Any questions? Okay, and that is not a tricky thing. Let me give you one last, let's say, vision of how sorted. Some of these examples you may know, you should understand. You need to know those are the bread and butter applications of sorting. There are other times when things happen, sorting becomes a building block of algorithms. And let me give you an example. There is a famous problem in geometry called finding the convex hull. This is the main problem in, the fundamental problem in geometry in the plane. You've got a bunch of points, and you want to find the smallest area polygon, okay, that contains all the points. If you look at these points, this polygon, this thing here, is the smallest area polygon that contains all of the points. The way I think of this is think of these points as being nails sticking out of the plane. And think of a giant rubber band you have stretched out to infinity that you let go and it goes ka-chung, right? What is going to happen with that rubber band? The nails are blocking it from going in further. Does everybody see that? If so, do you see that this shape is what gets formed from those points? How many people understand what I mean by convex hull? How many people don't and want me to explain it again? Should be somebody. I'm looking for a brave person. Okay? So finding what the smallest polygon is that contains these things is an important problem. How do you do it? Well, the real secret is you start by sorting. Okay? What if we sort the points by x coordinate? Suppose I add the points one by one in order of their x coordinate. Here is my next point. It has bigger x coordinate than anybody else, right? Is this point going to be one the rubber band is going to hit if I let go? Yes, right? So I know it's on the hull, right? So what's going to change with the hull? The new hull is going to look like the old hull with this point, with a chain of things removed, starting from the last point you have seen. Does everybody kind of get that idea? Okay? I don't want to give you the details, but you kind of see that something special happens. If I insert the points in random order, the next point might already be inside and not change my hull, right? But if I insert my points from left to right, I know that the one that I'm looking for is going to be on the outside. Okay? And then my problem is it's going to be really adjusting them by removing things. Okay? The details I don't really want you to see. Now, you can read in my book, I guess, if you really want to understand. Yeah, question. You can ask a question.
Does the problem mean to say smallest area convex polygon containing the wall?
It means the smallest area convex polygon. Is everybody? That's certainly true. Can anyone come up with a small polygon that isn't convex for these things? He's 100% right. If I didn't have the word convex in here. Again, I was trying to tip you off with the convex, but I need my polygon to be convex. Why? What's the smallest area polygon that contains all these points? Yeah?
Well, it contains a lot of depressions.
It'll contain zero area, right? Does everybody see that my polygon would look something like this?
Yeah, and that would double back on itself.
Right? So it has to be, that's not very interesting, right? But if it's convex, okay, then it has this nice property that we want, the rubber band ka-chung property. Any questions about that? But what I can tell you is, convex hulls are very important in geometry. The key to doing it in n log n time is the fact that sorting can be done in n log n time. And doing the fixing up of adding the next points, all of that fix-up can be done in order n time once you have sorted it. Okay? Any questions about it? It's just a basic premise that, again, sorting is the building block of many algorithms, and that's why we care about it. Any questions? Okay, good. So let's talk about some pragmatic issues associated with sorting. Again, that's actually maybe what I probably should have described it here. But read through this thing. You sort them points left to right. You insert them in order. You can correct them in an efficient way. And that's basically true. Any questions? Okay, so let's talk about the pragmatics of sorting. What I want you to be convinced about at this point. If the convex hull is disturbing you, forget it. You don't need to know about the convex hull. Okay? But you do need to know about these bread and butter applications of sorting. And let's just talk about some of the pragmatic issues with sorting. Okay? One thing to note is that all programming languages come with some kind of a sorting function or a sorting class or something like that. Okay? And making use of them requires knowing about the idea of a comparison function. Okay? What is the difference algorithmically between sorting something from biggest to smallest and smallest to biggest? Okay? Algorithmically, it is not a big difference. It is not a difference at all. The reason is because we are going to abstract the question of exactly what order you want by using some kind of a comparison function that given pairs of elements decides which should be in order before the other one. Okay? Again, if you look at a telephone book, you will often see that there are hard cases in alphabetizing, or certain decisions that get made when alphabetizing things that may seem a little bit weird or may seem kind of specific. So, for example, in alphabetical order, should Skeena with a capital S be before Skeena with a little s or not? And it depends upon your application. I don't know. Should Brown-Williams appear before Brown space America or after John, Brown? Does everybody see that if you make a decision to sort strings, you've got to make certain decisions about which order, how are you going to be treating some of these funny cases like punctuation? Okay? Should a comma be before a space? Should it be before an A or a Z or a digit? These are decisions you as an output person who's outputting using a sorting, you will have a desired order that you care about in principle. How do you ensure that the sorting algorithm know about your particular order that you want? Increasing or decreasing is a special case of this, right? Any questions about this? I really didn't explain that very well. But the way that you do it, in terms of sorting or using sorting libraries, is that we are going to assume your sorting library, okay? Whatever this is, IUC, this is my favorite sort function, okay? The important thing is that your sort function take as an argument a constant time function that that assumes a pair of the elements in the array and can make a decision of which should appear first in the array and which should appear last. Okay? Does everybody get this idea? The decision that you want Z to be before Y is a decision that is in some sense enforced by your comparison function. Yes?
The star inside the parentheses by the compare means that the function itself is the pointer, not that it returns a pointer to an integer.
So what the compare function does, actually, okay, now we're talking about C language, okay? And maybe I don't want to talk about C language too deeply. But what is this sorting? How does this sort work in C? Let me try to explain something, and then if you still have a question, you can ask. Qsort in C is a representative of a sorting thing. We say we want to sort an array which starts at a particular location. That is the first argument. Base here is a pointer to the start of your array. It says that each element in your array has a particular size, is a particular number of elements. Okay? This is what we mean by T-nel, the number of elements. Each element is a certain width, a certain number of bytes. If you know the number of elements, and the number of bytes per element, the number of elements times the number of bytes per element gives you the total size of the array. Knowing how many elements there are and how big the elements are enables you to figure out where the start of the ith element is. Now, what is this compare function? It says given pointers to two elements in the array, come back with a value. You have to provide it here. This is a pointer to a function. Okay, that's really what this is supposed to be referring to. A function that will tell you, is the first element before the second element in sorted order, or is the second element before the first element in sorted order? This comparison function is an argument you're passing to this that is going to make the decision for you for a pair of elements whether A should be before B or B is before A. Okay? And all the logic of the specifics of your application are encoded in that comparison function. Any questions about that? Okay? I realize I did a bad job explaining this. How many people understand what I said enough that they care about it? And how many people don't understand it? Okay, I'm seeing a bunch of people. Okay, so how would you specify, if you were a C programmer, okay, how to sort something? You would call Qsort, which is a built-in implementation of a fast sort function. And what would you give it? You would say, Qsort, I want to sort my array A. A is the name of my array. The name of an array is really given by denotes the first element in the array, the place in memory where that chunk of, that slab of memory starts. My second order argument is how many elements are there? Typically we use n to denote the number of elements in our array. Let's say our array has n elements. Suppose the elements in our array were integers. How many bytes long is an integer?
Size of int.
Okay, 4. Or if you want to be fancy C programming, there's a way in C it will tell you. So let's say I'll say size of int, or 4 if you know that, you're smart aleck and you want to write something that's going to break when they increase the size of the integer, right? Or, what's the last argument? You would like to give it a comparison function. And this is the name of a function that you wrote that will take 2 arguments, pointers to 2 elements, and tell you which should be first, right? So maybe compare is a function here, compare of A and B. I'm going to say if A is less than B, return 1, else return 0. Okay? And this is now going to return a 0, 1 value. The sort function is going to use this to decide for any pair of elements it compares which one is ahead of the other one. Okay? And this is how you would use a sorting library like Qsort in C in whatever language you use. Okay? There is going to be something like this. Some sort package, some sort function. And it's going to allow you to parameterize it by giving some kind of a comparison function, which you write, which for pairs of elements will decide what is first. Any questions about this? Okay, fair enough. Okay, so this is how you use a built-in sort library. And in general, built-in sort libraries are very good things that will do better than you will for many applications. Any questions? Okay, so what do we now know? The important things that we have learned today, and again, we're going to learn a little bit more, so don't reach for anything. We have learned that that sorting is very important, popular, used for a lot of things. We can use it for a lot of fundamental algorithm problems. We know that if we're going to use sorting in a real program, we should use a library function, and that we can get the effects, the issue of collating sequence or anything specific to an application is usually abstracted by that comparison function. And now we can start to get into algorithms for sorting. Any questions about that? So let me just talk briefly about one algorithm for sorting that you guys have seen a bunch of times and you hold in a certain level of contempt, called selection sort. What is selection sort? Can anybody describe for me what the selection sort algorithm is? Okay, somebody else, just for spreading the wealth. What is selection sort? Anybody know? Okay. No, you don't know. Okay. Okay. In a second. Wait a minute. Okay. Okay. Any questions? Okay. So what is the selection sort algorithm? The selection sort algorithm, okay, is doing what? You have a bunch of numbers you want to sort. Selection sort says go through the entire array till you find the minimum value here, right? Then swap the minimum value with the first element. Now you have a smaller array. The first element is in its proper position. Now you have a smaller array. And with that, you're going to, once you have the smaller array, you're now going to go through, you have a smaller array, and you're now going to repeat, find the smallest element in this array. Okay? What is the time? What happens in selection sort? It consists of two different phases. It is the first finding the smallest element in the array part that I'm interested in. The second thing it is pulling that element out, putting it in the first spot of the array, and continuing. How many people are with me at this point, what selection sort is? Okay? As you are used to implementing it, I claim selection sort is n times the cost of finding the smallest value plus doing the pulling out and putting it in the array. In normally implemented, how much time does it take to find the smallest element in the array? Yeah? The whole thing, I don't care about the whole thing. How much does it take to do this part of it? N. So in this case, it's n time. How much time does it take once you found the smallest to swap it with the first element?
Also order n.
Order n? Constant. Okay, it's just a matter of exchanging two values. Does everybody see that? So in fact, this algorithm is n times n plus 1, or order n squared. Does everybody see this? Now, if we used a better data structure that could do both of these operations quicker, okay, then we would have a faster algorithm. Yes?
And so the queue, or what's called priority queue, that can find the smallest log n.
So the important thing here is that there are faster data structures that we will talk about next time. Yes, hold on. So what if we put it in a binary search tree? That's an interesting idea. If we put it in a binary search tree, how fast would these operations take? How much time does it take if this was a balanced binary search tree? How much time would it take to find the smallest item there? Log n. And how much time would it take to delete it? Which is what it means to pull it out. How much time would it take to delete it? Log n. Does everybody see that? So using a balanced binary search tree, selection sort can be implemented in n log n time. It could also be implemented in n log n time using a simpler data structure called a heap, which I hope to talk about next class. Any questions about that? Question?
A bit interesting because binary search tree is always stored.
Wait, hold on. Questions?
Binary tree means actually it is already stored.
Binary search tree means, a balanced binary search tree means that all the items are stored in a tree of height order log n. That's what it means to be in a balanced binary search tree. Now, in a balanced binary search tree and sorting, there is a very close connection between them. That's what you're noticing there. Because the order inherent in a search tree is useful for sorting. Okay, any questions? Before you go, again, I have made the second homework assignment available. If you want to pick up a copy of the second homework assignment, my assistant will help you pass that out. Okay, if not, you can get it when you need it. Okay, thanks a lot. See you guys next class.
So what happened to the paperless office?